So this is the last and final part of chapter 3, which is Introduction to Organic Chemistry. So organic chemistry is a branch of chemistry that deals with the study of organic compounds and their chemical reactions. And these organic compounds basically contain the main two elements, which are carbon and hydrogen, but they can also contain other elements like oxygen, nitrogen, phosphorus, sulfur, and small amounts of other elements. Here are a few examples of organic compounds that are present naturally. So there's octane, which is basically an organic compound that's present in fuel. We have sugar, like glucose, sucrose, fructose, caffeine, and CBD, which is basically cannabidiol, okay, which is the one of the component of marijuana, right? So you have CBD oil and also the THC, which is the more potent component of marijuana. So these are all examples of organic compounds. And if you notice, these organic compounds, they contain the main two elements, carbon and hydrogen. And so what makes organic compound or what makes a compound an organic compound is that it has to contain at least these two elements, carbon and hydrogen. For example, carbon dioxide, right? Carbon dioxide is CO2. So it doesn't contain hydrogen. So we can't really categorize carbon dioxide as an organic compound because of the fact that it doesn't contain a hydrogen. So CO2 falls in the category inorganic compound and not organic compound. So carbon is the key element of organic chemistry. And the reason why is because their atoms, carbon atoms, can bond almost exclusively covalently. So what that means is that when carbon bonds with other elements, it can do so by sharing electrons, because that's what covalent bonding is. It's basically the sharing of electrons. Unlike ionic bonding is basically the transfer of electrons, usually from a metal to a non-metal, right? And because carbon is a non-metal, it has to bond covalently and not ionically. Organic compounds can be classified as either a hydrocarbon or a functionalized hydrocarbon. By definition, a hydrocarbon is an organic compound containing only carbons and hydrogens. And here are some examples. So we have CH4, which is methane. You have ethane, propane, butane, pentane, and so on and so forth. So all of these compounds, as you can see, based on their chemical formulas, they only contain carbons and hydrogens. Functionalized hydrocarbons, on the other hand, are compounds containing carbons and hydrogens as well as other elements in the periodic table, and they contain these special groups known as functional groups. And they have specific names. Like, for example, you can have an alcohol group, which is known as a hydroxy group. You can have an amino group, carboxyl, ester, thiol, and so on and so forth. So alcohols are examples of organic compounds. Ethanol is an example, methanol, propanol, and so on and so forth. You can have amino acids. They contain both the amino group and the carboxylic acid group. And that's why they're called amino acids. You can also have ester, like, for example, ethyl acetate. And thiols, like ethane thiol, in the industry, they're also known as mercaptans. In this chapter, we're only going to focus on hydrocarbons, plain hydrocarbons, and not functionalized hydrocarbons. So hydrocarbons can actually be categorized into saturated, unsaturated, and aromatic. So these three types of hydrocarbons are all different from each other. And because they're different, they would have different chemical structure, they have different physical and chemical properties. So by definition, saturated hydrocarbon is an organic compound containing carbon-to-carbon single bonds only. Okay, so what does it mean by a single bond? Well, when you look at a structural formula, right, a chemical structure, such as the one shown here, the bonding between the two carbon atoms are represented by only a single line. This one in red. Okay, so typically a single bond is represented by a single line, and it contains one pair of electrons. And that pair of electrons are being shared by both carbon atoms. So this is an example, or this is the chemical structure of ethane, okay, which is a saturated hydrocarbon. And they call it saturated because of the fact that the carbon atoms have the maximum number of hydrogen atoms that are bonded to them. Unsaturated hydrocarbons, on the other hand, they contain at least one carbon-to-carbon double and or triple bonds. Okay, so they are unsaturated because they don't contain the maximum number of hydrogens. Here's an example. This is ethylene, which is also a hydrocarbon. As you can see, it has two less hydrogens than ethane. So ethylene versus ethane on the left. And you can also see here that the carbon-to-carbon bond is a double bond, right? Because it's represented by two lines. If you have a triple bond, it would be three lines. So one line is equivalent to a single bond, and a single bond contains one pair of electrons. A double bond is represented by two lines, which equates to two pairs of electrons, and a triple bond contains three pairs of electrons, again being shared by the two atoms. Aromatic, on the other hand, is an example of a hydrocarbon containing single and or double bonds with ring structures. So basically you have carbon-to-carbon bonds, a bunch of carbons that are bonded together and forms a ring, a closed loop. Here's an example. So this is one perfect example of aromatic hydrocarbon. It's benzene. Okay, so you have alternating double and single bonds, and it forms a ring, a closed structure. And so if you look at the chemical structure here, you can see that it only contains, again, hydrogens and carbons, which makes this a hydrocarbon. And one main physical property of aromatic compounds is that they have a specific smell, right? Specific aroma. So perfumes contain aromatic rings, okay, aromatic structures. So that's all you really need to know about aromatic compounds. We're going to shift our focus on these two types of hydrocarbons, saturated and unsaturated. So both of these types of hydrocarbons can be categorized further into what they call families. All right, so saturated compounds, again, are compounds or hydrocarbons that contain single bonds, right? So the bonding between the two carbon atoms is a single bond. So these saturated hydrocarbons fall in the alkane family, spelled ALKANE. And I want you to take note of the suffix underlined here, ANE. So all saturated hydrocarbons will contain ANE in their chemical name. Okay, so I give you two examples here. The first one is propane. And as you can see in the name propane, it ends in ANE. The one underneath it is pentane. Okay, and pentane is a saturated hydrocarbon containing 5 carbons, and it also ends in ANE. The second type of hydrocarbon is the unsaturated hydrocarbon, and there are two families that fall in this category. You have the ones that contain double bonds and the one that contains triple bonds. The double bonds are the alkene family, So take note of, again, the suffix here. It ends in ene. Okay, so that means that the chemical names of all alkenes will end in ene. So an example is this one right here. So you have two carbon atoms with double bonds. So this is a perfect example of an alkene. And this compound is called dimethylbutene. So it ends in ene. And unsaturated hydrocarbons containing triple bonds are known as alkynes. And so the suffix ends in yne. So again, the chemical names of all alkynes will end in yne. Here's an example of an alkyne. So it contains two carbon atoms and with a triple bond. And this compound is called ethyne. So it ends in yne. But the common name actually ends in ene, and this is called acetylene. But based on the scientific name, it's actually ethyne. All right, so let's look at this practice question here. Based on the chemical structure, classify each hydrocarbon as an alkane, alkene, or alkyne. Okay, you can pause this video if you want to try it out yourself. So, by definition, an alkane is a hydrocarbon or a saturated hydrocarbon containing only single bonds. So, you can look at the second compound here. It only contains single bonds. And so, this is the only structure here that falls in this family, alkane family. Okay, so the first one over here contains a double bond and a single bond. So, because it contains a double bond, this falls in the alkene family. So the first one is alkene, the second one is an alkane, and the third one contains a triple bond. So it falls in the alkyne family. And the last one here, we have a single bond, double bond, and a triple bond, but because we have a triple bond here, this will fall in the alkyne family. Let's look at another practice question here. Based on the chemical name, classify each hydrocarbon as an alkane, alkene, or alkyne. So this one is kind of obvious based on the name because the suffix matches the family, right? So butane is the first one. It ends in ane. Octane also ends in ane. So both compounds, butane and octane, fall in the alkane family. We have methylpentene and propene. So you can see that they both have the suffix ene, which is basically an alkene. And the last one is heptyne, which falls in the alkyne family. So again, the first one is an alkane, and an alkene, another alkene, alkane, and an alkyne. So shown here are the 10 simplest alkanes. You have the chemical names on the left-hand side right here, and their chemical formula or molecular formula right here. And when you analyze the name, you can see that the suffix, right, ends in ane. So you have methane, ethane, propane, all the way to decane. And the prefixes also tell you how many number of carbon atoms that alkane contains. So, for example, when you look at the last 6 here, right? So pentane, hexane, heptane, octane, nonane, and decane. The prefix penta basically tells you that there are 5 carbon atoms. When you look at hexa, that means 6 carbon atoms, hepta 7, and so on and so forth. The first 4, you just kind of have to memorize them and remember them. So if you have a methane, that means you have single carbon. If you have ethane, 2 carbons, propane 3, butane 4. And the importance of the number of carbon atoms is in their physical properties. Like, for example, boiling point and melting point. The higher the number of carbon atoms, the higher the boiling point of that alkane. So, for example, when you look at methane and compare that with the boiling point of decane, right? So you can see methane boils at negative 161 degrees Celsius. So that means that at negative 161 degrees Celsius or higher, methane is going to be in gas form, right? So you can see that the first 5 here are basically in gas state, okay, or vapor state at room temperature, because room temperature is 25 degrees Celsius. And then all the rest from pentane all the way to decane, their boiling point, at least for pentane, is 36, right? So it's at least 36 degrees Celsius. And so they exist as a liquid. Octane is one of the active ingredients of fuel. And so this boils at 125 degrees Celsius. And so that means that below that, it's in liquid state. But the important information here is that the boiling point and the melting point increases as the number of carbon atoms increases. All right, so let's look at this one last example here. Rank the following linear alkanes in terms of boiling point. So you have 3 different alkanes here with specific number of carbons and hydrogen atoms in their chemical formula. So you have C12 versus C44 versus C25. And in terms of boiling point and melting point, the higher the number of carbon atoms, the higher the boiling point and melting point of that alkane. And so we know that C44 will have the highest boiling point and C12 would have the lowest boiling point.